Okay, welcome. There's two things that I want to talk to you about in this video. One, it's all has to do with atomic size. But in particular, one thing that we want to talk about is how do you define the size of an atom? Okay, so that can be tricky, and I want you to be able to, describe to somebody, in a couple of weeks exactly how chemists go about defining atomic size. The second thing that I want you to understand by the end of the video is sort of the overall trends in atomic size. So that is, if you're looking at a periodic table and I randomly pick two elements on the periodic table, you should be able to give a pretty good guess for which one is larger, and then describe how atomic size changes going from top to bottom as well as left to right. Okay, well, first thing, I want to just help you appreciate how difficult it is to measure the dimensions of a single atom. So right here on the screen, I've got a hydrogen atom, and so there's the proton, there's the little guy. The electron cloud is, I'm depicting it, and I tried to draw like a spherical distribution. This is the 1s orbital, as you guys remember from the last unit. So that one electron of hydrogen, there's a pretty good chance that you're going to find it within this region of space, right? But in reality, there is a chance. Let me draw, like if we go way over here, for example, and we draw a little box. So let's say we take our electron detector way out here, and we measure. We kind of station that detector there and try to look for electrons. Well, you're not going to find the electron way over there very much, but every once in a while you will pick up a trace of an electron over there. So the point is that even though this space represents the highest probability region for finding the 1s electron, there is a very small chance that you will find it way out here and over here in these nether regions. So it's tricky. It's very tricky defining the boundary of an atom, because electrons are, they're kind of shifty. They spend most of their time here, but every once in a while, they're gonna jump out here. Sometimes you'll see books where they will define what's called a 90% probability surface. And so basically you can think of that as just like a ball, right? That within which the electron spends 90% of its time, okay? And so some people define the atomic radius like that. There's another way to do it, though. And I'll show you how, probably a more accepted way where most of the atomic radii come from. So the scientists discovered that there's a lot of elements that will bond with each other, with other atoms of the same element. And here's 7 examples, all right? These 4 down here are the halogens. Hopefully you recognize these as being in the group 7A. And what you can do is, if the same 2 elements are bonded to each other, then if you come over here and look at this diagram, you can see that there's this very well-defined distance between the 2 nuclei of the bonded atoms. And this distance is something that scientists can measure very accurately. There's a number of different experimental techniques that can determine this internuclear distance, and if you can do that, I think you can see, like from the geometry of the diagram here, that 1/2 of the distance between those 2 nuclei is the atomic, or a good definition of an atomic radius. Okay, and so you can see that there's quite a variation in atomic radius. So hydrogen is very small, 30 picometers, all the way to iodine, 140 picometers. Okay, so now we kind of understand how atomic radii can be measured, and then how we define it. Okay, so with that definition in hand, we can go on to the second part of our objective, which is what are some of the trends among the elements in atomic size? Okay, well, if you had to just boil this all down to a post-it note, here's what you need to know right there. So as you go from top to bottom within a group or a column, the atomic size increases. And as you go left to right, across a row or a period, atomic size decreases. Here's a fairly detailed description of how atomic size varies as you go from hydrogen way down here all the way, and they did, for this particular graph, they went all the way up to element number 55, which is cesium, way up here. Okay, and so what they've done is they simply ordered the elements by atomic number, so they're plotting the atomic number on the X, and then on the Y, they're plotting atomic radius. And it's very interesting, some of the trends that you see, right? So hydrogen, as you would expect, very small, 30 picometers. Then when you get to helium, a little bit bigger. But then, look what happens when you go from helium to lithium. This huge jump, it jumps, it increases over 3 times. So if you think carefully about the electron configuration, this big jump actually, isn't so surprising. So you know that the electron configuration of helium is 1s2, right? Then the third electron has to go into the 2s orbital, right? And so that's the next principal energy level higher. And we know that when electrons go into higher energy orbitals, they tend to live, a lot further away from the nucleus. And so that's one reason why you see these big jumps between the noble gas element and then the next element back over in group 1a. So these elements that are labeled in yellow, these are, I think, if you look at your periodic table, and you should have your periodic table open at the side as you're watching this, because you'll need it. You'll notice that lithium, sodium, potassium, these are all elements in the group 1a. Okay, these are the alkali metals, and then down here are labeled the noble gas elements. Okay, and then the last thing I want you to notice is that, for example, when you are at lithium and you start going across the second row, period 2, there's this contraction in the radius, right? It goes down very quickly. So we go from 150, 155 for lithium, all the way down to, like maybe 62 for fluorine. So there's this really substantial contraction in the size of the atom as we go across the periodic table. All right, here's a here's a little bit more global view. Here's the whole periodic table. This is just to summarize. Just try to remember the atomic size decreases as you go left to right, and it increases going top to bottom. Now, at some point, we're going to need to be able to, that is, you will need to be able to describe clearly what is the reason that elements increase in size as we go from top to bottom. And then we're also going to be able, you're going to have to be able to describe why do the atoms shrink, why do they get smaller as we go left to right. Okay, well, the left to right trend, I'm just going to tell you, it's a little bit subtle, it's a little bit involved, and we're going to get into that in a later video. But for right now, I think you are in a very good position to understand why the atoms get bigger as we go top to bottom. Okay, so here we go. So in the n equals 1 energy level, that's period 1. Hydrogen is the first element, and you can see that if we depict the element here with with the Bohr model rings for each principal energy level, you've only got one ring here, right? So that's n equals 1. But then when we go down the group to the next period, that electron, the third electron, is in the n equals 2 energy level. So we've added another a whole nother principal energy level. So that's like the next ring. And then as we keep going down, sodium, the electron number 11, that is going into the n=3 energy level, and so on. And so I think you can see as we step down the group here that the reason these atoms are getting bigger and bigger and bigger is because we're adding more and more energy levels. And as you go up in energy levels, the radius gets much bigger. So that the top to bottom trend is pretty easy to understand. The left to right trend, that's a little bit more challenging, and we'll get to that. Okay, so to wrap this up, let me just throw a couple atom pairs at you, and let's just see if we can quickly identify which atom is bigger based on what we just talked about. Okay, so you've got your periodic table open, hopefully. You need to locate boron and oxygen, and let's see if we can figure out which one's bigger. Okay, so here's my table, and here are the two elements on the table. And if you remember that the atoms are getting smaller as we go left to right, then that would lead us to decide that boron is bigger, right? And when you look up their actual radii, you can see that indeed boron is about 12 picometers larger than oxygen. All right, how about boron versus aluminum? Okay, what do you think? So again, now this is an easy one. Aluminum is directly below boron, so aluminum must be bigger, because the trend is atoms get bigger as we go top to bottom, and sure enough, it is. All right, how about fluorine versus chlorine? All right, so again, we've got another, upstairs, downstairs pair, but this is over in group 7A, but same thing. Chlorine should be larger, and it is. Okay, phosphorus versus oxygen. Now this one is slightly trickier because it's not a really clean comparison, right? Because phosphorus is not only is it not in the same period as oxygen, it's not even in the same group. However, you can be reasonably assured that because phosphorus is below oxygen in the periodic table, it's in a higher period, and it's to the left. Because it's to the left, it should be bigger. Because it's lower, it should also be bigger. So we should be on pretty safe ground that we should be able to safely say phosphorus is bigger, and indeed it is. Okay. Now, finally, last one, lithium, which has 3 electrons, versus astatine, which has 85. Okay, if you can find astatine, it's if you can find fluorine and chlorine on your periodic table, astatine is way down at the bottom of group 7A, so it's right below iodine. So yeah, interesting. Astatine has 82 more electrons than lithium. So, surely it must be way bigger, right? I mean, look how many periods. It's in period 6. Lithium's only in period 2. So all those shells must be contributing to a much larger radius for astatine, right? Well, actually, you'd be wrong. This is kind of surprising. Actually, astatine is just a little bit smaller than lithium. And so the last thought I want to leave you with is that, as you go left to right, this contraction of radius is, very pronounced, despite the fact that it has way more shells than lithium. Okay, guys, I hope that helped, and I'll see you at the next video. Thanks.